Today's lesson, we are going to do some preparation for the probability state standards 1 and 2. And our objective for today is to specify a sample space and events for random experiments. So we start out with some definitions. And our first definition is a definition of a random experiment. This is an experiment where you don't get the same outcome when you repeat the experiment under the same conditions. Three good examples of this would be flipping a coin, rolling a die, which is singular, not paradise, but that would work as well, or choosing a card from a standard deck of cards. A sample space is listing all the possible outcomes in a set for that random experiment. So for a coin, for example, flipping that, you can only get two outcomes. You get heads or tails. So we might represent the sample space as the set H, T, where H represents the heads, T represents the tails. And if you were rolling a die, a standard and fair six-sided die, the sample space would be the set 1, 2, 3, 4, 5, 6. Those are the only possible outcomes for rolling a die. So sample space is the set of all outcomes. An event is a subset of this complete sample space set. And we're doing it for a subset for a particular experiment, and we're going to do some of those examples in a moment. And a simple event is when there's only a single element involved in that sample space. So for instance, at the beginning of a football game, you flip a coin once, heads or tails, whoever calls it decides who's going to kick off or receive. So let's start looking at a few examples. First example says when you're rolling a single die, and this is three problems in one. So the first one, part A, tell us the sample space. Part B, list the event that the number is less than 4, or list the event that we get an even number. So as we said, the total sample space for rolling a die is the set 1, 2, 3, 4, 5, 6. So for a standard and fair six-sided die, that's our sample space. Those are all the possible outcomes. So for part B, we want the number less than 4. So we're just going to take our sample space, list all the numbers less than 4. So the sample space for this event is 1, 2, and 3. And as we said, any event is a subset of the possible outcomes. What about an even number? Well, there's only 3 even numbers on that single fair six-sided die. You can get a 2, a 4, or a 6. Now let's talk for a moment about rolling a pair of dice. When you have 2 dice, we're going to have 6 outcomes from the first die, 6 outcomes from the second die. And remember, we learned in a few lessons ago the fundamental counting principle said we multiply those. So we've got 6 outcomes from the first, 6 outcomes from the second. When we roll a pair of dice, there are 36 possible outcomes. One way to represent this is to think of each roll of those 2 dice as an ordered pair. So for example, the ordered pair 5, 2, instead of being an x and y value that we're plotting on a graph, 5 would be one die, 2 would represent what we got when we rolled the other die. So if we represent these 2 dice as a set of ordered pairs, this represents our sample space. We could get a 1 with a 1, a 1 with a 2, 1 with a 3, 1 with a 4, 1 with a 5, 1 with a 6, 2 with a 1, 2 with a 2, 2 with a 3, 2 with a 4, 2 with a 5, 2 with a 6, etc., etc., etc. We could get a 6 and then a 1, a 6 and a 2, a 6 and a 3, all the way through a 6 and a 6. So there is our listing of our sample space for our 36 possible outcomes. So what we're ready to do now is to do an experiment, do an event. We're going to roll 2 dice, specify for part A the sum of the numbers of the dice equals 5. So what we need to do is look through the list and find all the numbers, or ordered pairs in this case, where we get a sum of 5. And that would be, we could get a 1 on the first die and a 4 on the second die. Conversely, we get a 4 on the first die and a 1 on the second die. Or we can get a 2 with a 3, and then we could also get a 3 with a 2. So there are 4 possibilities in this particular event. Now, part B says, well, the first die is a 3, which means they're not specifying what the other die could be. So we could get a 3 with a 1, 3 with a 2, 3 with a 3, 3 with a 4, 3 with a 5, or 3 with a 6. So those would be the sample spaces representing the events. And probability, continuing with our definitions, is a measure of how likely an event is going to occur. We have what we call equally likely outcomes if both events have the same chance of occurring. So for example, when we flip a coin, heads and tails are equally likely. And this is what we call theoretical probability. We're going to be working with that instead of experimental probability. Experimental, you would flip the coin and determine, yes, it came out heads, yes, it came out tails, and you do it enough times that in theory we would get the same number of heads as we would get the same number of tails. So in this case, for equally likely outcomes using theoretical probability, the probability that any event may occur is a ratio. So remember, ratio is another way to say we're going to have some kind of fraction, perhaps. And it's the favorable or desired outcomes, so what you want to happen, over the total number of outcomes. So it might be written as this: P for probability, and they might describe the event in words, or there might be a capital letter representing the event. Could be P of A, and then they described A as representing whatever event it was, P of B, etc. So it's what you want over what's possible. Number of favorable or desired outcomes over all the outcomes in the sample space. Now, just so you know, there are other books out there that will call these favorable or desired outcomes successes. And if you're not getting one of those, they'll call it a failure. So you might see it written in this kind of notation. Probability of success, your desired or favorable, is how many ways you can get that success over the total outcomes in your sample space. In this case, they're saying that's represented by the sum of the successes and the failures. Probability of a failure, then, is how many ways you can get a failure or not get what you're looking for over the total outcomes in your sample space, which they define as the successes and the failures. So again, the total number of outcomes is in the denominator, no matter what notation you use, and what you're wanting or desiring or your favorable outcome is in your numerator. When we get these probabilities, we can write them in three different formats. We can write them as fractions or ratios. We can write them as decimals. We can write them as percents. If we use fractions and decimals, we're going to have greater than or equal to 0 and less than or equal to 1. Percent, greater than or equal to 0% and less than or equal to 100%. So it's going to look something like this. The probability of any event, we're going to use a capital letter, E, to represent any particular event, is greater than or equal to 0 and less than or equal to 1. If we do get 0, we say the probability of that event is impossible. If we get the probability of that event equals 1, we say it's certain to occur. And again, if they're equally likely, we say probability of one event is equal to the probability of the other event. All right, let's look at another example. I know this one's a little bit older. You're probably not listening to music on CDs, but on some kind of portable player. But let's say that a particular music CD has 5 songs that are your favorite and 7 you don't like as much. And if you hit that randomize button on your CD player or your music player, what's the probability that a randomly selected song turns out to be one of your favorites? Well, denominator, there are 12 possible outcomes. Why? Because there are 12 songs on the CD. There are 5 what we call favorable or desired outcomes, because there are 5 of your favorite outcomes. So the probability then of getting one of your faves is 5 out of 12. So the probability of getting this event, one of your favorite songs to play, is 5 out of 12. If we use a calculator and write that as a decimal, that's 0.417. Or if we go for percent, that's 41.7%. We'll see problems like this frequently on the STAR testing. We've got bags of marbles, and of course the implication is we can't see through the bag. So we have to randomly select one. In this particular example, there are 4 red marbles, 6 blues, 3 yellows, and 2 greens. And if one is chosen at random, the question is, what's the probability that it's blue? Well, for our denominator, there are 15 possible outcomes because there are 15 marbles. 4 plus 6 is 10, plus 3 plus 2, 15 marbles. And the probability that it's blue, there are 6 blues. So the probability of drawing a blue marble randomly is 6, because there are 6 blue marbles, out of 15, because there's 15 marbles in total in that bag, which when you divide that out in your calculator, you get 0.4, which is the same as 40%. So you've got a 40% chance of drawing the blue marble randomly. All right, what I'd like to do for a moment is talk about playing cards, because it seems that students these days not every student knows what a standard deck of cards consists of. So there are 52 cards in the deck if we take out the jokers, which we usually do. They're organized in 4 suits, what we call them. There's pictures of spades, clubs, diamonds, and hearts. Each suit has 13 cards in it. There's an ace, there's numbered cards 2 through 10, and then there are 3 what we call face cards, where we see a picture of a jack, a queen, and a king. So yes, there are 13 cards too. You might see, and then hearts, then diamonds, then clubs. Again, each one has an ace, a 2 through 10. And I know these are a little hard to see, but a picture of a jack, a queen, and a king. Now, normally I would reserve this for class, but I'm going to do this one as well here in the lecture, because I want to do a little experiment with the deck of cards. So what's the probability of randomly drawing a red card from this standard deck of playing cards? So we're going to do this one together. There are 52 cards. So our denominator, there are 52 possible outcomes. And as we said, there are 13 cards in each suit. So we've got 13 red diamonds, 13 red hearts. So there are 26 red cards in the deck. And that's what our favorable outcome here is, to get a red card from the deck. 26 out of 52 will reduce to a 1 out of 2 chance. As a decimal, that's 0.5. And as a percent, that's 50%. So today, our goal was to get us prepared for these probability state standards 1 and 2. We needed to get some definitions out of the way: sample spaces, events, simple event, compound event. We pretty much covered that. It's definition of probability, what it means to have equally likely outcomes. And that pretty much concludes this particular lesson. We will continue on this in our next lesson as we continue our pursuit of probability.